Okay, so this is section 7.2, which is all about sums and differences of sines, cosines, and tangents. So basically, we're going to be using these three formulas. Well, there's actually six formulas. Sine of x plus or minus y is equal to sine x cosine y plus or minus cosine x sine y. There's the first two. So the book writes these as two separate formulas. I'm just condensing them using the plus or minus. So if the input in here is x plus y, then over here this sign will be a plus. And if it's x minus y, then this sign will be a minus sign. Then there's cosine of x plus or minus y. So x and y here are just angles. X and y are just angles here. Cosine x times cosine y, and then minus plus sine x sine y. So I'm using minus plus here because the sign is opposite. If it's plus inside, if it's x plus y, then this sign will be a minus sign. That's why the plus minus is flipped upside down. And if it's x minus y, then this sign will be a plus. And then there is tangent of x plus or minus y, and that's going to be equal to tangent of x plus or minus tangent of y. So the signs match here, but then they are opposite in the bottom. 1 minus plus tangent x tangent y. So if this is plus in here, if it's x plus y, then this sign will be a plus and this sign will be a minus. If it's minus in here, x minus y, then this will be a minus and this will be a plus. Okay, basically what this section is all about is a bunch of different ways we can use these formulas, or these identities, and then the last two examples in this section are about actually sums of sines and cosines. So not a sum inside, but a sine something plus cosine something, and a new formula for that, or a new set of identities that allows us to graph sums of sines and cosines. But we'll get to that later. So the first example, and I'm just going to walk through the textbook examples and probably just provide more parts to each example than they do. So they say find the exact value of the expression. So this is one of the most useful ways, or one of the most useful uses of these formulas, is that we can take the cosine of some angle that we don't know, that's not a familiar angle, right? The familiar angles being are 0 degrees, 30 degrees, 45 degrees, 60, 90, etc. 135, 180, 120, all the multiples of these. So I'll say etc. 75 is not there, but we can write 75 degrees as, what can we write it as? We can write it as a sum of 30 plus 45. So you've got to get a little creative and just sit there and think about it for a minute, like which of these angles, or multiple of these angles, can I add or subtract to get 75? And sometimes there might be more than one way of doing it. Well, there's always I suppose, many ways of doing it. Usually one way will stand out, though. usually one way. Like this one kind of jumps out at me, writing 75 as 30 plus 45. So over here, instead of cosine of 75, I can write it as cosine of 30 degrees plus 45 degrees. But now I have a sum inside of the input of my cosine. So I'm going to use my formula, and it says that cosine of 30 degrees plus 45 degrees is equal to, using this formula, cosine x, so x is 30, y is 45 here, so cosine of 30 degrees times cosine of 45 degrees minus sine of 30 degrees sine of 45 degrees. And now each of these we can evaluate. Each one of these four terms we can actually evaluate. So cosine of 30 degrees, let's see, 30 degrees is the small angle, so this is 1. So cosine is 1/2. And then cosine of 45 degrees is square root of 2 over 2, or 1 over square root of 2. And then minus, now sine of 30 degrees, oh dang, I messed this up. Sine of 30 is the 1/2. This is square root of 3. Whoops. Yeah, cosine of 30 is square root of 3 over 2, adjacent over hypotenuse. Okay, and then sine of 30 is opposite over hypotenuse. There we go. And then sine of 45 is going to be root 2 over 2. And then the idea is to clean this up. So we're getting square root of 3 times square root of 2 is square root of 6 over 4 minus root 2 over 4. And that's giving us, we can write that as square root of 6 minus square root of 2 all over 4. And, oh, I'm off the page. There we go. Square root of 6 minus square root of 2 all over 4. And I can't actually subtract these because they're not like terms. They're not the same radical term. Okay, part B for example 1, cosine of pi over 12, cosine of pi over 12. So I want to write this as, I want to write pi on 12 as the sum or difference of some familiar angles. And for in terms of pi, my familiar angles are going to be 0, pi on 6, pi on 4, pi on 3, pi on 2, and then multiples of those, 2 pi on 3, 3 pi on 4, 5 pi on 6, and etc. So I'm thinking of what can I write pi on 12 as, and I'm thinking, what about pi over 3 minus pi over 4? That will do it, because this is 4/12 minus 3/12, so this is what I need. So I'll write cosine of pi over 12 as cosine of pi on 3 times cosine of pi on, oh, I skipped. I'm writing pi on 12, so I'm writing cosine of pi on 12 as cosine of pi on 3 minus pi on 4. Pi on 3 minus pi on 4. And then that is turning into this. So I'm going to have cosine of the first one times cosine of the second one, and then plus, because the sign is changing, for the cosine, the sign is changing, and then I'm going to have sine of pi on 3 times sine of pi on 4. Okay, now I need to evaluate each one of these. Pi on 3 is that 60-degree angle, so this is 1 root 3 and 2. So cosine of pi on 3 will be 1/2. And then cosine of pi on 4, that's the 45-degree one. That one's square root of 2 over 2. And then plus sine of pi on 3 is opposite over hypotenuse, so square root of 3 over 2. And then sine of pi on 4 is square root of 2 over 2. And now we just need to clean this up. I'm getting square root of 2 over 4 plus square root of 6 over 4. And then that can be written as square root of 2 plus square root of 6 over 4. And that's it. That's all we can do. There we go. Alright, next one. Let's see. Sine of 75 degrees. Sine of 75 degrees. Well, I can write 75 the same way that I wrote it before, as 30 plus 45. So I'm going to say that this is the same as sine of 30 degrees plus 45 degrees. And then that, now I'm using the sine formula, so I need to make sure I'm using the correct orientation, the correct order for the factors. So it's going to be sine x cosine y plus cosine x sine y. So I'm going to have sine of 30 degrees times cosine of 45 degrees plus cosine of 30 degrees times sine of 45 degrees. And that's going to give me, let's see, sine of 30 degrees is 1/2, and then cosine of 45 is square root of 2 over 2. Cosine of 30 degrees is root 3 over 2, and sine of 45 degrees is root 2 over 2. And then cleaning all this up, I'm going to end up with square root of 2 over 4 plus square root of 6 over 4, which is equal to square root of 2 plus square root of 6 all over 4. All over 4. So very similar answer. And it's a similar answer because so far all of these angles have been very similar. All of them are involving pi on 4 and either pi on 6 or pi on 3. Alright, let's do part D. Sine of 19 over 12 pi. So I need to figure out how am I going to write 19 over 12 pi as some recognizable angle. Let's see. What about... So one way to think about this, if you're stuck trying to figure out what angles to use, is think about your special angles like pi on 4 and what that equals in terms of this denominator. So pi on 4 is 3 pi on 12. And then you may say, okay, if I used this, what else would I need? I would need, to get to 19 over 12, I would need 16 over 12. So is there some other angle that is equal to 16 over 12? And surely this looks good. This looks like I can pull a 4 out of both of these. If I pull a 4 out of both of these, I'll be left with 4 over 3. And these are both nice special angles, this one and this one. So what I can do is I can write 19 over 12 as 3 over 12 plus 16 over 12. In other words, I can write 19 over 12 as 1/4 plus 4/3. And I have information about this angle and this angle. So sometimes it's helpful to think of the special angles with that in terms of the denominator that you're actually looking at. It's not as big of an issue when your angle is in degrees. It's much easier to think about when the angle is in degrees. But when you're dealing with fractions, you've got to be a little bit more creative. So what I'm going to do is I'm going to say sine of 19 over 12 pi is equal to sine of pi over 4 plus 4 pi over 3. Plus 4 pi over 3. Okay, and then that's going to give me sine of pi on 4 times cosine of 4 pi on 3 plus, so I'm using my identity now, plus cosine of pi on 4 times sine of 4 pi on 3. Okay, so I know what sine and cosine of pi on 4 are, but I'm thinking of where is 4 pi on 3, and I know that that's going to be in that third quadrant because it's past a whole pi. 3 pi on 3 would be the whole pi, and then it's a little bit further, or a whole third further. So it's in the third quadrant where both of these sides should be negative, and let's see, it's going to be 1 and 2 and root 3. There we go. So sine of pi on 4, that's square root of 2 over 2. Now cosine of 4 pi on 3 is going to be adjacent over hypotenuse, so negative 1 over 2. And then plus cosine of pi on 4, that one's easy, that's root 2 over 2. And then sine of 4 pi on 3 is going to be opposite over hypotenuse, which is negative root 3 over 2. Let's see. Yeah. Okay, cleaning all this up, I'm getting negative square root of 2 over 4 minus square root of 6 over 4, which can condense to negative root 2 minus root 6 all over 4. Okay, one more with tangent. How about tangent of 165 degrees? So I need to think of how to write 165 degrees. I could say maybe 180 and 15, taking 15 away from 180, but 15 is not a special angle. So I could do 120 and 45 and write them as a sum, and I think that's going to be a good idea. So I'm going to say tangent of, what did I say, 120 degrees plus 45 degrees. So this is pi on 4 for 45 degrees, and 120 is 2 pi on 3. But we're in terms of degrees, so... Okay, now for tangent, I've got a weird formula that's a fraction. First of all, in the top, I'm going to have tangent of the first, 120 degrees, plus, where is it, tangent of the second, 45 degrees, over 1 minus tangent of 120 times tangent of 45 degrees. So I need to know what each of these are. Let's see, 120 degrees, well, I know tangent of 45 is going to be 1, so these are both going to be 1. But 120 degrees is in the second quadrant, and that's going to be, this side is negative, this side is positive, and my hypotenuse is 2. And tangent of 120 should be opposite over adjacent. So I'm getting tangent of 120 is negative square root of 3, opposite over adjacent, plus 1, that's tangent of 45, is 1. Then 1 minus tangent of 120 is opposite over adjacent, so I'm getting negative square root of 3. So this will clean up nicely to 1 minus square root of 3, that's the top, just flipping them around. 1 minus square root of 3 over 1 plus square root of 3. Oh, this could actually rationalize really nicely because we could multiply in the top and bottom by 1 minus root 3, but do we need to do that? Probably not. This is fine. Let's see, if I did it anyways, just in case we need to do that, you would multiply by 1 minus root 3 in the top and bottom, which is going to give you 1 minus 1, 1, and then this, they'll cancel, and then I'll have this times this, so minus 3. And in the top, I'll have 1, let's see, minus 2 root 3 plus 3, which is going to give me, let's see, a negative 2 in the bottom, and a 1 plus 3, so 4 minus 2 root 3 in the top. Okay, so the next example is going to be working backwards. It says find the exact value of, we'll call this part A, sine of 20 degrees, cosine 40 degrees, plus cosine of 20 degrees, sine of 40 degrees. So they're basically asking us to line this up with one of the formulas and write it in this form. So it's got to be sine of x plus y. That's the formula we're dealing with here, where x and y are 20 and 40, so we've got this is all equal to sine of 20 degrees plus 40 degrees, but that's equal to sine of 60 degrees, and that's pi on 3. There we go, there's the root 3, so root 3 over 2. There we go. So all they want from us here is basically using the formula in reverse. And then how about one with tangent? So tangent of pi over 18 plus tangent of pi over 9 over 1 minus the product of those. Well, this is equal to, according to the formula, tangent of, so we're looking at this formula, we've got a plus in the top and a minus in the bottom, which means there must be a plus inside. So we've got tangent of x plus y, where x is pi on 18, and y is pi on 9. And this is equal to tangent of, getting a common denominator of 18, this would be 2 over 18. So we're getting 3 pi over 18, 1 over 18 plus 2 over 18. But that simplifies to pi on 6, and tangent of pi on 6 is 1/2, right? Let me make my little triangle. Here's root 3, 1, 2. Oh, no. That's 1 over root 3. 1 over root 3. Opposite over adjacent. There we go. 1 over root 3. Okay. That's all they're asking for here. Just kind of going in reverse. Okay. Another use of these formulas is we can prove these cofunction identities. So we'll just prove one of them because they all kind of go the same. And remember, the cofunction identity basically relates sine and cosine directly. Actually, we're going to do 2 of these. Prove the cofunction identity. Cosine of pi over 2 minus u is equal to sine of u. This is basically saying that cosine and sine aren't really that different. One is just shifted. And you see that in the graphs too. If you look at the graphs, if you take the graph of cosine and shift it forward, or you could take either one and shift either one by pi on 2, then you'll have the exact same graph. And that's all that this is saying here. Where, by the way, u is the letter playing the role of the angle here. So they want us to prove this by using one of these, specifically the cosine of x minus y, because we have x minus y here where x is pi on 2 and y is playing the role of u. So we're going to use this formula. So if it's minus inside, we should have plus connecting on the right side of our formula. So we should have this side is, let's see, I'm going to bring the equal sign down. I'm not going to mess with the right side, because remember, when you're proving an identity, you work both sides, but sine of u, there's not really a lot to do there. So I'm going to work this left-hand side. I'm going to have cosine of x, the first thing, cosine of pi on 2, times cosine of u, and then plus sine of pi on 2 times sine of u. Okay? Now notice cosine of pi on 2 is 0, so this whole term here goes away. 0 plus sine of pi on 2 is 1, and then times sine of u. But that checks out, because 0 plus 1 times sine of u is just sine of u. Okay, and how about another one? Where is it? Yeah, this one's pretty interesting. They pretty much all go the same way, but these cosecant, cotangent, and secant ones are a little different just because of the way we define these as reciprocal functions for cosine and sine. So I'm going to rewrite this as 1 over cosine of pi over 2 minus u. This should be equal to 1 over sine of u. This is what I'm now trying to prove. But I already found that cosine of pi over 2 minus u is equal to sine of u. So just by all of these previous steps here, that would all just be happening in this denominator, I'm going to end up with 1 over sine of u is equal to 1 over sine of u. So it basically works exactly the same, except everything's upside down and in a denominator. And really, just by showing these two, this will work for all of the cofunction identities, going from cosine to sine and sine to cosine, cotangent to tangent, tangent to cotangent, secant to cosecant, and cosecant to secant. They'll pretty much all work like this, where one of the terms will zero out. Okay. Example 4 is another identity, just a different kind of identity. So we want to verify the identity of 1 plus tangent x over 1 minus tangent of x is equal to tangent of pi over 4 plus x. Oops. Tangent of pi on 4 plus x is what that says. Okay, so let me rewrite it over here so I have some room. 1 plus tangent x over 1 minus tangent x. Actually, let me go ahead and write tangent of pi on 4 plus x with my formula for tangent. So tangent of x plus y is giving me tangent of x plus tangent of y all over 1 minus tangent of x times tangent of y. So using that formula where x is playing the role of pi on 4, and this x is playing the role of y, so that's a little confusing, but that's what's going on here. I'm going to have tangent of pi on 4 plus tangent of x, that's the top, all over 1 minus, and then the product of those, pi on 4. There we go. But tangent of pi on 4 is 1. So this cleans up super nicely to say 1 plus tangent of x over 1 minus 1 times tangent of x, which is just tangent of x. So I clearly get equality here. And you can prove all sorts of different weird identities like this using these sum and difference identities. Let's see. Okay, example 5 is just a weird one. I really doubt that you'll see something like this in the homework or on an exam. But just in case, I'm going to work it out. If f of x is equal to sine x, show that f of, so this difference quotient, f of x plus h minus f of x all over h is equal to sine x times cosine of h minus 1 all over h plus cosine of x times sine of h all over h. Ooh, yeah. If you've heard of the hyperbolic sine and cosines, that's not what's going on here. Hyperbolic sine and cosines are a different kind of trig function. You guys may not have even have talked about them. But just so you know, that's not what's happening here. This is cosine of h and sine of h. And the reason I'm even bringing that up is for those hyperbolic trig functions, h is involved in defining those. But that's not what's going on here. H is only involved here because it was involved on this side of in the function. And this is a special quotient that you see in calculus. You don't need to worry about it right now. Okay, so we're supposed to say that if f of x is equal to sine of x, then plugging that in here will give us all of this. I'm going to work from this side. I think I'm just going to work one side because this side is so big. I'm just going to work with this and try and get in the end to get it to match this. So if I have f of x plus h, that's going to be sine of x plus h, because sine is my function, and then minus sine of x, and then all over h. So I'm just working this side, and I'm going to work this side this way. Sine of x plus h, I have a formula for that. That's going to be sine of x times cosine of h plus cosine of x times sine of h, and then minus sine of x all over h. And I think that's basically it. We just need to do some algebra to clean this up to get it in the form they want it in. So let's see. If I look at these two terms, this term, sine x cosine h, minus sine x, if I factor a sine x out of those two, I'm going to be left with cosine h minus 1. So that's taking care of this and this. And then, because I'm factoring a sine x out of both of them, right? So sine x gets detached from this cosine h, and sine x gets detached from this minus sine x. That's why I've just got a minus 1 there. And then the last term that's left, that middle term, is cosine x sine of h, and this is all over h. Which, if it's all over h, I can split the fraction and say this is over h and this is over h. That's fine. And that's basically what they want, except they just want me to write it as sine x times, just storing the h under just this part of the fraction for this first term, which is fine. That's a legitimate algebraic thing to do. And similar thing happening here, just storing this h under just the sine of h. So really, though, the work really comes from right here, plugging in your function and then using the sum identity to expand. And then from here down is just reordering things with algebra, cleaning things up. Okay, so that's a strange example, but the book deemed it important, so I didn't want to skip it. Okay. Example 6. Let's see, example 6. Okay, Yes, these are weird. Okay, right. I'm going to say this is part A. Right sine of cosine inverse of x plus tangent inverse of y as an algebraic expression in x and y. So we don't want any trig functions left. Whoops. In x and y. And then they're telling us the bounds on x. This is just to make sure that we don't mess up our trig functions and plug numbers that aren't allowed in there. Okay. So x is just bounded because it's plugged into cosine, and y is not bounded because it's plugged into inverse tangent. Or I should say x is bounded because it's plugged into inverse cosine, so we know that the domain of that needs to be bounded, but the domain of inverse tangent does not need to be bounded. So that's why x is between -1 and 1, and y can be any real number. So this part's not really important. This is just to make sure we don't get any undefined stuff in our problem here. So this is a weird problem. What's going on here is x is a side and y is a side of a triangle. And so we're going from, we want to go from giving a side to this function that then turns it into an angle, because that's what cosine inverse does, and then sine out here will take that new angle and turn it back into a side. So we want to kind of get rid of all that, because what this function is doing right now is we're going from side to angle to side, but we want to kind of skip those first two steps and get straight to just a function or an algebraic expression just in terms of the sides. We don't want to involve, there's too much trig involved here and it's redundant. We don't need all of this extra trig in here because it's redundant. So one of the first things that you have to do, though, is recognize that this and this are angles. Cosine inverse of x, that it outputs an angle. That's what an inverse trig function does. It outputs an angle, and similarly with tangent inverse. So we name them as angles and just give them angle names. And we don't want to use x and y for the angle names because x and y are already taken, so the book uses theta and phi. So that's the Greek letter phi. Okay. You may see it more like that, but I draw mine like that. Okay. Now, if I define them as angles, then I can say, well, what else can I say? I can rewrite this much more cleaned up as sine of theta plus phi, right? Because I'm just replacing cosine inverse with theta and tangent inverse with phi. Just direct substitution there. But I have a formula for this. It's a sum inside of a sine function, so I can say this is sine of theta times cosine of phi plus sine of phi. Well, we usually write it the other way. It doesn't matter, but let's stick to the... Okay, cosine of theta times sine of phi. Now the problem is, I don't know what any of these are. These are all four new trig functions, and I don't know what any of these are going to equal. So what I need to do is I need to figure out what each of these are. So first let me say, if theta is equal to cosine inverse of x, then cosine of theta is equal to x. And similarly with tangent of phi is equal to y. That's just inverse trig function business. That's if we have this relationship, then we have this relationship. And if we have this relationship, then we have this relationship. Now, if I know cosine of theta, then I can find sine of theta. Because I want to get all of this in terms of x and y, right? So I got cosine of theta, that's x, but I need sine of theta. But I can find that if I think about how this triangle looks. If this is theta right here, cosine is given as adjacent over hypotenuse. So my adjacent side must be x, and my hypotenuse must be 1. My hypotenuse must be 1. And what I need is sine of theta, so I need sine theta. But sine of theta is opposite over hypotenuse. So what's the opposite side? Find opposite. Well, Pythagorean theorem. That's how I'm going to do it. I need this side. So I'll call it b. So a squared plus b squared is equal to the hypotenuse squared. So that these are the two legs, x and b, and the hypotenuse is 1. And I'm going to solve for b. So b squared will end up being 1 squared is just 1, and then minus x squared, and that's going to give me b is equal to square root of 1 minus x squared. So there's my missing side. So sine of theta, now it looks bad, it's ugly, it's not a nice clean number, but it's in terms of x, and that's what I want. Sine of theta is opposite over hypotenuse, so sine of theta is going to be this opposite side over 1, which is just going to be 1 minus x squared. And there we go. We've got cosine theta, which we need right here. Cosine theta is just x, and we've got sine theta. So now we need cosine of phi and sine of phi. So let me draw a new triangle with phi, and if tangent of phi is equal to y, then this is opposite over adjacent, and this is opposite over adjacent. So we're going to have y over 1, so opposite over adjacent, there we go. And now I need to find the hypotenuse, and in a similar way, the hypotenuse will be y squared plus 1. Square root of y squared plus 1, just by working the Pythagorean theorem again. So, I need sine and cosine of phi. Sine of phi is going to be opposite over hypotenuse, so y over y squared plus 1. And cosine of phi is going to be adjacent over hypotenuse, so 1 over y squared plus 1. Now I have all the pieces I need. I've got cosine of theta, I've got sine of theta, I've got sine of phi, and I've got cosine of phi. Those are the 4 pieces that I needed. So I've got sine of theta plus phi is equal to, so working from here, sine of theta is square root of 1 minus x squared. Cosine of phi is 1 over y squared plus 1 under a square root. And then I'm going to have plus, and then cosine of theta, which is just x, and then sine of phi, which is y over square root of y squared plus 1. And this can be cleaned up a bit to, I've got a common factor of y squared plus 1 under a radical in both denominators, so I can actually factor that out. Factoring 1 over y squared plus 1 out, and that's going to leave me with square root of 1 minus x squared, that's the first term, plus, and then what's left if I factor 1 over y squared plus 1 over square root of y squared plus 1 from this term, it'll just be xy. There we go. So these are a bit tricky. But really the technique that to me is most important is that very first thing, renaming these inverse trig functions as angles. Because once you do that, then it starts to become apparent what you need to do, what you need to find, and how you need to find it. Let's do another one like that. Example 6b. So same instructions with cosine of sine inverse x minus tangent inverse y. Okay, so let's just go ahead and name those inverse trig functions. There we go. So we've got cosine of theta minus phi, just renaming. And then that's going to be cosine of theta times cosine of phi plus, I'm using my difference identity for cosine now, sine of theta times sine of phi. So these are the four things I need. These are the four things I need. So let me start with this relationship. If theta is equal to sine inverse of x, then sine of theta is equal to x, and that's going to give me this triangle. So that's actually one of the four already done, right? If sine of theta is equal to x, that's this one, sine of theta. So this one's done. I need to find these three. And in particular, with this triangle I'm about to make, I'm going to be able to find cosine of theta. So if sine of theta is x, that's opposite if this is theta. Opposite over hypotenuse. You need to solve for this missing leg using the Pythagorean theorem, and you'll get square root of 1 minus x squared, very similar to the last problem. And now that means that cosine of theta is going to be adjacent over hypotenuse, so 1 minus x squared under the square root. Okay, so that's this and this done. Now I need to look at phi, but I've given this relationship involving tangent, so I know that tangent of phi is equal to y, which is not as directly as helpful as sine of theta equal to x, because tangent is not involved here. But that's still okay, we can still build our triangle from this. So there's phi. And if tangent of phi is equal to y, then that's opposite over adjacent, so that's going to be y over, opposite over adjacent, y and 1. And then our hypotenuse will be y squared plus 1 under the square root by the Pythagorean theorem. And then that's going to give us that sine of phi is opposite over hypotenuse, so y over y squared plus 1. And cosine of phi is adjacent over hypotenuse. So this one's looking very similar to the last one. Alright, now we have all four pieces, so cosine, rewriting this, cosine of theta minus phi is equal to cosine of theta, where are we, is square root of 1 minus x squared. Cosine of phi is 1 over square root of y squared plus 1, plus sine of theta is just x, and then sine of phi is y over square root of y squared plus 1. Is this exactly the same? It's exactly the same. It's the exact same answer. Because we're going to have 1 over square root of y squared plus 1 times square root of 1 minus x squared plus xy, factoring out this 1 over y squared plus 1 under the radical. So it ended up being exactly the same. Let me look and make sure I didn't mess something up. Oh, no. It's because over here, the difference is, there's two differences, and they're canceling each other out. The difference here is sine is on the outside and cosine's on the inside. And here, it's the opposite. Cosine's on the outside, sine's on the inside. And tangent is constant in both of them. So that's the same in both of them. The other difference is this, plus and minus. And those two differences are just enough. They're so similar and just different enough that they actually worked out to be exactly the same. Oh well. Okay. So, next two examples. Oh, no, one more example using these sum and difference identities. Let's see, evaluate, call this A, sine of theta plus phi, where this is an interesting problem, where sine of theta is equal to 12 over 13. So this time they're telling us exactly what the ratio of these sides is, and theta is in quadrant 2, and tangent of phi is equal to 3 over 4, and phi is in quadrant 3. Okay. Well, let's see. This is kind of similar in that we're going to start with this sum identity. We're going to write this out as sine of theta times cosine of phi plus cosine of theta sine of phi. And then we're going to realize, oh, well, I've got sine of theta, it's 12 over 13, but I don't have cosine of theta, and I don't have cosine of phi or sine of phi. So the idea is we're going to draw the triangles again and find these missing sides, but we're not going to have to go through the algebra of finding those missing sides with the Pythagorean theorem just in terms of x and y. We're going to have actual numbers to deal with here. Actual numbers. So they tell us that sine of theta is equal to 12 over 13, and theta is in quadrant 2. So quadrant 2 is over here, so something like this. And so here's theta, where this side is negative and this side is positive, and sine is 12 over 13, that's opposite over hypotenuse, so we have 12 over 13, opposite over hypotenuse. We need to find this missing side, so I'll say, I think it's 5, right? It's 5. So you can work the Pythagorean theorem and make sure that it is 5, but you get 5, and it's negative because theta is in quadrant 2. So what did I need from this? I needed cosine of theta. And cosine of theta is opposite over... Sorry. Cosine of theta is adjacent over hypotenuse, so I'm getting negative 5 over 13. And that's all I needed from theta, because I've already got sine theta, and now I've got cosine theta. So now I'll work on phi. So now, new triangle for phi. Phi is in quadrant 3, so I'll just draw it down here somewhere. This is phi. And I've got both of these sides, by the way, are negative in quadrant 3. That's why they tell us what quadrant these angles are in, so we know what the signs are on these sides. And tangent of phi is equal to 3 over 4, so that's going to tell me opposite over adjacent. So negative 3 and negative 4 there. And I'm going to need to find this hypotenuse, and by the Pythagorean theorem, you'll end up finding that it's 5. And it's positive. The hypotenuse is always positive. And I need both sine of phi and cosine of phi. I need both of these. I need sine of phi and cosine of phi. Let's see, cosine of phi is going to be adjacent over hypotenuse, so negative 4 over 5, and this one will be opposite over hypotenuse, so negative 3 over 5. And now all that remains is to plug each of these in. So sine of theta came from the actual problem, so 12 over 13. then times cosine of phi, which is negative 4/5. So you just want to make sure you're not getting mixed up here. Just make sure you're plugging in the right thing. Cosine of theta is negative 5/13. And then sine of phi is negative 3/5. And now you just need to clean this up a little bit. Let's see, we're going to have negative 48 plus 15 all over whatever 13 times 5 is, 65. And then this will be negative 33/65. Right, yeah, there we go, that's it. So it's pretty similar to the previous example, except that we have actual numbers instead of just x and 1, or y and 1, and these weird square root things. We have actual numbers to work with. But you do got to be careful about the signs now. They're telling us where the angle is in what quadrant, so you got to be careful about these signs. Okay. So, example 8. Example 8 and 9 deal with sums of sines and cosines. So, now we're talking about things in this form. A times sine of x, no, is it x? Yeah, plus b times cosine of x. And we know that, according to the book, that this can be written as k, some number k, times sine of x plus some angle phi. And this is really useful for, for graphing, for one. If you have a sum of a sine and a cosine, you can condense it down to one in terms of just sine, and you can graph this. Amplitude is here, you'll have a phase shift here, etc. Okay. So, what are the relationships, though, between k and a and b, and phi and a and b? Well, k is easy. K is just going to kind of act like the hypotenuse if a and b were the legs. So it's going to be the square root of a squared plus b squared. And phi is going to be not so straightforward. Cosine, they give us this relationship for phi. Cosine of phi should be a over k, and sine of phi, so you got to get k first. Sine of phi should be equal to b over k. And by the way, this a is always attached to sine, so this is the number attached to sine over k, and this is for sine. This is the number attached to cosine, so they're flopped. You see that? Okay. So let's practice using this relationship. So express 3 sine x plus 4 cosine x in this form. And graph. Wait, is that, no, not yet, not graphing yet. Okay. What do we need to do? We need to find k and phi. Well, k is going to be equal to the square root of 3 squared plus 4 squared, which is a pretty common relationship, and we're just going to get 5 there. We're going to get 5, so k is 5. Now we need to find phi. Cosine of phi is equal to a over k, and sine of phi is equal to b, which is 4 over k. So what this tells us is that phi is positive. Phi is in the first quadrant because both of these are positive. And that's going to be important because what we're going to need to do now is use calculator, because this is not like 1 over 2 or square root of 3 over 2 or square root of 2 over 2. This is not some common ratio of sides that we know about. This is some weird angle. So we need to use the calculator, and it should give you that phi is approximately 53.1 degrees by using cosine inverse on this, or sine inverse on this. So you'll plug in cosine inverse of 3/5. And it's important to note that it is positive, right? Because remember, the tricky business about using a calculator with inverse trig functions is the calculator only knows where the function is defined, but angles do not obey what a function says, right? Angles are more free. So we have to know what quadrant this angle is in, but since both of these are positive, we know that our angle is in quadrant 1. So we get that, and this is all we need. Now we are ready to write it in the form k times sine of x plus 53.1 degrees. There we go. Okay, b. I'm going to do a second example with this b. Where is it? Oh, negative square root of 3 times sine of x plus cosine of x. Alright, so a here is equal to negative root 3 and b is equal to 1. These are the coefficients attached to each of these. So k is the square root of a squared plus b squared, and that's going to be square root of 3 plus 1, square root of negative square root of 3 all squared is just 3, and then 1 squared is 1. So I'm getting square root of 4, which is 2. Now I also know that cosine of phi should be a over k, which is going to give me negative root 3 over 2, and sine of phi should be b over k, which is 1 over 2. But what does this tell us? What does this tell us? Where is cosine positive and sine... where is cosine negative and sine positive? Where is cosine negative and sine positive? In quadrant 2, right? In quadrant 2. So we just need to keep that in mind. But we don't need a calculator for these, because we know these are special ratios that we know about. So what must phi be? Is it the pi on 2 pi on 3? Well, let's see, that would give me, this would be negative 1 and root 3 and 2, so it's not that one, otherwise yeah, it's not this one, so it's got to be the other one, which is, this is negative root 3, this is 1, and this is 2. There it is. That will give me the correct relationship between the sides here. And what is that angle? That is one of the pi on 6 angles, right, because it's a tiny angle, and it's 5 pi on 6. 5 pi on 6. So writing this, I've got k is 2, and I've got my angle, so k times sine of x plus phi. There we go. Okay, so the last example is about taking a sum of a sine and a cosine and writing them in a form that we are able to graph. So let's write f of x, which is equal to negative sine of 2x plus square root of 3 times cosine of 2x in that form, k times sine of x plus phi. Oh, it's got to be 2x plus phi. Yeah, that's right. Because our input is 2x. We're just matching the input there, 2x. And graph. So we don't know how to graph f of x in its current form, because it's a sum of a sine and a cosine. But if we can get it in this form, then we can graph it. Okay, so first we need k. K is going to be equal to square root of a squared, which is -1, plus b squared, which is square root of 3, all squared. And that's going to be square root of 1 plus 3, which is square root of 4, which is 2. So k is 2 again. And then we have cosine of phi is equal to a, which is -1 over 2. And sine of phi is equal to b over 2. So this is some coordinate point, -1 over 2, comma root 3 over 2, corresponding to some angle, and that should give us phi is, it's actually the first one I drew last time. It's 2 pi on 3. This one, right? 2 pi on 3. Where, yeah, because adjacent is -1 over 2 and opposite square root of 3, so yeah. 2 pi on 3. So the form that I want f written in is f of x is equal to k times sine of 2x plus 2 pi on 3, which I could also write as 2 times sine of, factor this 2 out so that I just have x plus something, pi on 3. And that way I can more easily identify the phase shift here, and the period. Because remember, in the overall form, when you're identifying amplitude and especially period and phase shift, you have to factor this number off of the x and the number that's being added or subtracted. So what I've got here is I've got an amplitude of 2 because of that 2. I've got a period of it's 2 pi over this number, which I think is called b if you look back at graphing trig functions, 2 pi over b or whatever they called it. So that's giving me a period of pi, so that means my graph is squished. Its period of sine is usually 2 pi, a full 2 pi, but now it's squished to half of that. And then my phase shift is pi on 3 to the left, so I'll say negative pi on 3. Negative pi on 3. So I want to graph this. Oh, let's see, okay, 1, 2, 1, 2. So here's 2. I'm drawing out to 2 because my amplitude is 2. And my period is pi. Let's see, this is going to be kind of tough. So between here and here, I should cycle a full time, so like that. But I'm supposed to be phase shifted by pi on 3. What I'm going to do is, just to make it easier on myself, I'm going to graph without the phase shift, with the amplitude of 2 and the period of pi. I'm going to graph that with a dotted line, so it would be like up and then down, like that, and similarly over here. Oh, that's kind of ugly. Should hit there. And then my actual graph should be this same thing, but shifted that way by pi on 3, which is going to put it, let's see if I can do this. Let's see. I'm doing my best, but I don't know. Oh, that doesn't feel quite right. I may need to look at, let's see, okay, so, and then, oh, maybe too far, oof, rough, something like that. Oh, that should be touching too. Okay, something like that. Yeah, so I just looked at the one in the book, and it should be like, oh, I really messed it up. Should be scooted, this should be squished a little bit more. But anyways, that's the basic idea. The point is that with a function given in this form, you can write it in this form, and that lets you graph it. And that is it.